Weight and balance is one of the most fundamental responsibilities of any pilot or aviation professional. Before a single flight takes place, understanding how weight is distributed across an aircraft and ensuring it falls within approved limits is essential to safe and legal operation. In this chapter, we'll cover the core principles that govern weight and balance, starting with why it matters and what can go wrong when limits are exceeded. We'll explore the effects of excessive weight, the critical role of center of gravity, and how regulatory requirements define the boundaries within which every flight must operate. By the end of this chapter, you'll also be able to work through the computational methods used to determine whether an aircraft is properly loaded before flight. These aren't just theoretical concepts. They're practical skills applied on the ground before every departure. Let's get started. Weight and balance is one of the most critical pre-flight responsibilities a pilot has, and understanding why it matters goes beyond simply following rules. When we talk about structural integrity, we mean that every aircraft is engineered to handle specific stress loads. Exceeding the maximum allowable weight puts forces on the airframe that it was never designed to withstand, which can lead to structural failure, sometimes with little or no warning. Performance is equally affected. Excess weight degrades takeoff distance, climb rate, cruise speed, range, and landing performance across the board. There are no exceptions. Then there's controllability. The center of gravity, or CG, must remain within the manufacturer's approved limits throughout the entire flight. If it falls outside those limits, the aircraft may become difficult or impossible to control. Remember this fundamental relationship. Weight is the force of gravity acting on the aircraft's mass, and lift is the only force that opposes it. Lift is constrained by airfoil design, angle of attack, airspeed, and air density. If you load the aircraft beyond the recommended weight, you may be asking it to generate more lift than it is physically capable of producing. At that point, flight itself is compromised. This is why weight and balance is never optional. It is a safety-critical calculation every single flight. Overloading an aircraft has serious and wide-ranging consequences that every pilot must understand before departure. When an aircraft exceeds its maximum gross weight, performance degrades across every phase of flight. Takeoff requires a longer ground roll and a higher rotation speed. Once airborne, the rate and angle of climb are reduced. Maximum altitude is lower, range is shorter, and cruising speed and maneuverability both suffer. Perhaps most critically, stall speed increases, meaning approach and landing speeds must be higher, and the landing roll will be significantly longer. What makes overloading especially dangerous is how it compounds other risk factors. At high-density altitude, for example, the aircraft is already operating with reduced engine and aerodynamic performance. Add excessive weight to that equation and safety margins can disappear entirely. Pre-flight planning must always include a thorough review of performance charts to confirm the aircraft is within limits. And this is a decision that must be made on the ground, because once you are airborne, your options are extremely limited. If an engine fails on takeoff or ice begins forming on the airframe at low altitude, there is no way to reduce weight in time to recover. The consequences of overloading, including excessive weight on the nose wheel or tail wheel, must be fully considered before the flight ever begins. When managing aircraft weight, two major sources of change deserve careful attention: fuel load and equipment modifications. Starting with fuel, gasoline weighs 6 pounds per U.S. gallon. That means 30 gallons of fuel can easily outweigh a passenger. If you're considering reducing fuel to bring the aircraft within weight limits, keep in mind that this directly impacts your range, and that trade-off must be accounted for during flight planning. Once airborne, fuel burn becomes the primary in-flight weight change. As fuel is consumed throughout the flight, the aircraft becomes lighter, and you'll generally see a gradual improvement in performance. On the equipment side, any installation of additional radios, instruments, repairs, or modifications can have a measurable impact on overall aircraft weight. These aren't just maintenance considerations, they have real implications for weight and balance. Every change of this nature must be properly documented in the aircraft's weight and balance records, and the equipment list must be updated to reflect the current configuration. Failing to record these changes means your weight and balance data is no longer accurate, which can compromise the safety of every subsequent flight. Always treat weight and balance documentation as a living record that reflects the aircraft exactly as it currently exists. The center of gravity is one of the most critical concepts in aircraft weight and balance, so let's make sure you have a solid understanding of what it means and why it matters. The center of gravity, or CG, is the single point at which the entire weight of the aircraft acts downward. Think of it as the balance point. If you could suspend the aircraft from that exact location, it would hang perfectly level. For flight purposes, we're primarily concerned with the fore and aft position of the CG along the longitudinal axis. When the CG is too far forward, the aircraft becomes nose-heavy. The pilot will struggle to raise the nose during takeoff and flare during landing, which can lead to hard touchdowns or runway exceedances. When the CG shifts too far aft, the situation becomes even more dangerous. The aircraft loses longitudinal stability and may become extremely difficult or impossible to recover from a stall or spin. Lateral imbalance is also a concern, typically caused by uneven fuel loads between wing tanks. This creates a wing-heavy condition, increases drag, and reduces overall efficiency. Every aircraft has published CG limits, both forward and aft, found in the Type Certificate Data Sheet, the Airplane Flight Manual, and the pilot's operating handbook. Operating within those limits is not optional. It's a safety and regulatory requirement. Understanding the forward and aft center of gravity limits is essential for safe flight operations, and knowing how each affects aircraft behavior can be the difference between a routine flight and a dangerous situation. The forward CG limit is typically determined by landing characteristics. When the CG is too far forward, the aircraft becomes nose-heavy. This increases loads on the nose wheel, raises stall speeds, and demands higher control forces throughout the flight. In extreme cases, the pilot may not have enough elevator authority to flare properly for landing, a potentially catastrophic outcome. The aft CG limit is perhaps the more dangerous of the two. As the CG moves rearward, the aircraft becomes progressively less stable. It loses its natural tendency to return to level flight after a disturbance. Control forces become dangerously light, stall characteristics can turn violent, and recovery may become difficult or impossible. As the pilot in command, you directly influence where the CG falls. Thoughtful decisions about passenger seating, baggage placement, and fuel management all matter. If your aircraft is tail-heavy, seat your heaviest passengers forward. When selecting fuel tanks, remember that tanks located near the CG have minimal impact on balance as fuel burns off, making them a useful tool for maintaining a stable CG throughout the flight. Before we move into calculations, it's essential that you have a firm grasp of the core vocabulary used in weight and balance work. These terms will appear throughout every problem you solve, so let's walk through them carefully. The datum is your starting point, an imaginary vertical reference plane that the manufacturer establishes. Every arm measurement originates from this location, which is also called Station Zero. The arm, sometimes called the moment arm, is the horizontal distance in inches from the datum to an item's center of gravity. Arms measured aft of the datum are positive, while those measured forward are negative. When you multiply weight by arm, you get a moment expressed in inch-pounds. The moment tells you how much rotational force that item exerts around the datum. Add all your moments together and divide by total weight to find where the center of gravity actually falls. The CG range defines the forward and aft limits certified as safe by the manufacturer. Staying within that range is not optional. It's a legal and safety requirement. You may also encounter CG expressed as a percentage of MAC, or mean aerodynamic chord, which represents the average chord length of the wing. This is common on larger or more complex aircraft. Finally, know the difference between useful load and payload, and commit the standard fluid weights to memory. Gasoline at 6 pounds per gallon, Jet A at 6.8, oil at 7.5, and water at 8.35. The foundation of all weight and balance work comes down to one essential formula. To find the center of gravity, you divide the total moment by the total weight. That result gives you the CG location, which must fall within the aircraft manufacturer's certified CG range before the aircraft is considered safe to fly. Operating outside that range can critically affect stability and controllability. Understanding where measurements come from is equally important. Every arm measurement references a fixed point called the datum, which is an arbitrary reference point established by the aircraft designer. It might be the nose of the aircraft, the firewall, or even a point ahead of the aircraft entirely. It varies by make and model. What matters is the sign convention. Items located aft of the datum carry a positive arm value, while items located forward of the datum carry a negative arm value. Multiplying each item's weight by its arm gives you its moment, and once you have all the moments, you sum them and divide by total weight to get your CG position. Master this formula and you have the core of every weight and balance calculation you will ever perform. Let's walk through a complete weight and balance calculation using the computational method. In this example, our aircraft has a maximum gross weight of 3,400 pounds and a center of gravity range of 78 to 86 inches. We begin by listing every item that contributes to the loaded weight of the aircraft. The empty weight is 2,100 pounds at an arm of 78.3 inches, giving us a moment of 164.30 inch-pounds. We then add our front seat occupants at 340 pounds, rear seat occupants at 350 pounds, 75 gallons of fuel at 6 pounds per gallon for a total of 450 pounds, and 80 pounds of baggage in Area 1. Once all weights and moments are entered, we total both columns. Our total weight comes to 3,120 pounds, and our total moment is 281.430 inch-pounds. To find the loaded center of gravity, we divide the total moment by the total weight. 281 on 430, yes, divided by 3,220 gives us approximately 84.8 inches. Now we check against our limits. The total weight of 320 pounds is below the 3,400 pound maximum, and the CG of 84.8 inches falls within the acceptable range of 78 to 86 inches. This aircraft is loaded within limits and is safe to fly as configured. Now let's look at those graph and table methods for working weight and balance problems. These approaches are commonly found in pilots' operating handbooks and offer a visual, intuitive way to verify that your aircraft is loaded within limits. The loading graph, shown as figure 10-7 in your materials, simplifies the process of finding moments. You locate each item's weight on the vertical axis, draw a horizontal line across to that item's specific load line, and then read straight down to find the moment divided by 1,000 on the horizontal axis. You do this for every item: fuel, passengers, baggage, then total all the weights and all the moments. Once you have those totals, you move to the CG envelope graph, figure 10-8. You simply plot your total weight against your total moment, and wherever those two values intersect tells you immediately whether the aircraft is within acceptable limits. The envelope will typically show boundaries for both normal and utility category operations, so you can see at a glance which category applies to your planned flight. The table method in figure 10-9 works on exactly the same principle, but removes the need to plot anything. Instead, the manufacturer provides pre-calculated tables showing the minimum and maximum allowable moments for each possible weight. You simply look up your total weight and confirm your total moment falls within the range provided. When working with weight and balance, you'll encounter three common scenarios: shifting existing weight, adding new weight, or removing weight entirely. Understanding how each affects your center of gravity is essential for safe flight planning. When you shift weight, the total weight of the aircraft stays the same, but the moments change. Moving weight aft increases the total moment, which moves the CG aft. Moving weight forward decreases the total moment, shifting the CG forward. When you add weight, the new CG moves toward the station where that weight was added. Think of it as the CG being attracted to the new load. When you remove weight, the opposite happens. The new CG shifts away from the station where the weight was removed. A practical tip to remember: when shifting weight aft, add the change in CG to your old CG value. When shifting forward, subtract it. Before you finalize any calculation, take a moment to mentally verify that the direction your computed CG has moved actually makes sense given what you did. This quick logical check can catch arithmetic errors before they become a serious problem. Let's walk through 3 practical worked examples that show how weight changes affect your center of gravity. In the first problem, we have an aircraft weighing 7,800 pounds with a CG at 81.5 inches, which is behind the aft limit of 80.5 inches. We need to shift cargo forward from station 150 to station 30. Using the shift formula, we find that moving just 65 pounds forward brings the CG exactly to that 80.5-inch aft limit. A relatively small weight shift can make a significant difference. In the second example, we start with a 6,860-pound aircraft at a CG of 80.0 inches. Then, we add 140 pounds of baggage at station 150. Applying the addition formula, the CG moves aft by 1.4 inches, giving us a new CG of 81.4 inches. Always verify that this new position remains within your approved envelope. In the third example, we remove 100 pounds from station 150 on an aircraft weighing 6,100 pounds with a CG at 80.0 inches. Removing weight from an aft station moves the CG forward, and in this case by 1.2 inches, resulting in a new CG of 78.8 inches. Notice how adding and removing weight at the same station produce opposite CG movements. Understanding these relationships is essential for maintaining a safe, balanced aircraft. Understanding the regulatory framework behind weight and balance is essential for every pilot and aviation professional. These requirements aren't arbitrary. They exist because operating outside approved limits can compromise aircraft controllability and structural integrity. Title 14, CFR Part 23, Section 23(3) places the responsibility on the manufacturer to define the safe operating envelope. The resulting weight and CG ranges are published in the Approved Flight Manual, the Type Certificate Data Sheet, or the Aircraft Specifications. These are your authoritative references. Part 91, Section 91.9, then shifts responsibility to the pilot in command. While Part 91 does not explicitly require a written weight and balance calculation before every flight, it absolutely requires compliance with the published limits. Ignorance of an exceedance is not a legal defense. For larger commercial operations, Part 125 and Part 135 aircraft must be physically weighed every 36 calendar months, and weight and balance records must remain current following each 100-hour or annual inspection, as outlined in Advisory Circular 43-131. Finally, not every minor equipment change triggers a full weight and balance revision. Negligible weight thresholds, 1, 2, or 5 pounds depending on aircraft size, and negligible CG shift criteria provide practical guidance for determining when a formal recalculation is actually required. As we wrap up Chapter 10, let's reinforce the core principles that every pilot must carry into every pre-flight. Weight and balance is not an administrative checkbox. It is a fundamental safety requirement. Always verify your aircraft's weight and center of gravity before departure. Never assume a standard passenger load or typical fuel configuration keeps you within limits. The numbers must be confirmed every single time. Remember that operating overweight degrades every aspect of performance: climb rate, takeoff distance, stall speed, and your available safety margins all move in the wrong direction simultaneously. Center of gravity location matters just as much as total weight. A forward CG makes the aircraft difficult to flare and land properly, while an aft CG creates dangerous instability and unpredictable stall behavior that can quickly exceed a pilot's ability to recover. You have 3 computation methods available: the computational method, the graph method, and the table method. All 3 are built on the same foundation. Weight multiplied by arm equals moment. Use whichever method your specific aircraft's AFM or POH provides. As the FAA states, pilots must ensure the CG is and remains within approved limits throughout all phases of flight. Weight and balance is not just a pre-takeoff concern. It applies from engine start to shutdown.